Hey everyone, welcome back. In this video we're going to talk about the thing that we left off with at the end of the last lesson, which was, so we had an equation of a line that we got after quite a lot of work, but we got the equation of the line to look something like y equals 2 over 3 times x minus 4 over 3. And this was the equation that we got from the graph of the line that we drew. So if you remember, first we used the 2 points that we were given to find our slope, and then what we did is we took our slope and one of the points, and I believe the point was, what was it? Was it 1? I think it was -1, -2 was the point that we ended up using. And we took the x-coordinate, this -1, and we subbed it in place of the x, and we took this -2, and we subbed it in place of the y, and then we used, that's a terrible arrow, but then, so we plugged in the -2 over here, we plugged in the -1 over there, and so we had numbers everywhere except for over here, and then we used those numbers to calculate the y-intercept, which is b. And so ultimately we came up with the equation y equals 2/3 x, that should be minus 4/3. So that was the equation that we ultimately came up with, and what we left off with was I rewrote that equation in this form over here, in this box right here. And my question to you is, why is this still a valid way to write down the equation of a line? Because it doesn't look anything like y equals mx plus b that we've been working with so far, right? So this is the form that we're comfortable with, and we talked about how you can move around things a little bit. I could have written this as like b plus xm, for instance, and it's still the equation of a line. I could have swapped their sides. I could have used different letters, so I could have done something like, I don't know, I could have done something like b plus ax equals y or something. And that's still the equation of a line, but it also still looks something like what we started with over here. But what we've got up in the box, it looks totally different from anything else that we've got. So why is this still a valid expression for the equation of a line? So basically what I'm saying is, why, if you tried to plug this into one of those websites that can graph a function for you, why is this still going to give you a line instead of giving you something that looks like, so if you've got your Cartesian plane, why is it still going to give you a line instead of giving you something that looks like this, or something that looks like that, or I don't know, something else entirely, something that like goes like this and then drops off and then reappears over there? Like, you could have a whole bunch of crazy functions doing a whole bunch of different things. Why don't we see any of that if we try to plot this equation up here, even though it looks different from everything we've seen so far? And the reason for that is we're still only dealing with y's and x's. We're not dealing with y squared or x squared or the square root of either of those. We're not doing anything with logarithms, which we talked about a couple of units ago. Yeah, I think a couple of units ago we talked about logarithms. So like, if we were trying to graph something like y is equal to x squared, or y is equal to the square root of x, or y is equal to the logarithm of x, if we were trying to graph any of these things, oops, you can't see that bottom one. If we were trying to graph any of these things, we would get a graph that looks different. Even if we were trying to graph something like y equals 1 over x, something like that, would give a different looking graph. But as long as you're dealing with just y's and x's, they're not in the denominator like this x over here is. So they're not in the denominator of a fraction, and they're only being multiplied by other numbers. They're not being multiplied by each other. They're not being squared. They're not being square rooted. There's no logarithms involved. If there's none of that other stuff, there's no sines or cosines, if you guys remember from trigonometry from last year. If we're not seeing any of those other things, you're still going to get the equation of a line. So now my last question relating to the last video is, how did we get from that equation to this one? Or how do we get from this one to that one? So on a test, I could give you something like this one here in the box, and ask you to graph it. And it would be a little bit mean for this particular question, unless I give you exactly this question, because we've already worked with this one. But so I could give you this equation and say, graph it for me. But we don't know how to graph an equation that looks like this. We know how to graph an equation that looks like that. So if I've given you this one, and I ask you to turn it into a form that looks like that one so that you can graph it, we got to be able to do that. So the first thing we want to do is, we don't want anything to be in brackets over here. So what I'm going to do is, I'm going to use the distributive property, which we talked about a while back. And so basically I'm going to take this 2 that's sitting here on the outside, and I'm going to multiply it by each term inside. So I'm going to multiply it by the x, I'm going to multiply it by the 2, I'm going to leave that minus sign in the middle, and we're going to get rid of the brackets. So if I rewrite this, we get 3y is equal to, and then if I do the distributive property for the on the right side, I'm going to get 2 times x, so that's 2x, and then I'm going to get 2 times 2, which is 4, and we're going to keep the minus sign in the middle, so we've got it like this. So we've got 3y is equal to 2x minus 4. We still don't quite know how to graph this, but at least that right side is looking a lot more familiar now, right? This is looking a lot more like something that you would see in the equation of a line, right? If you were looking at your y equals mx plus b, you'd be able to identify, okay, this is my m and this is my b, but the problem is, we want it to be y equals mx plus b, not 3y. So our only remaining step is, we want to get this to be just y. So in order to do that, I'm going to divide this side by 3 so that the 3's cancel, but if I'm dividing by 3 on this side, I have to divide by 3 on that side. So I can divide by 3 like this. So then if we do that, and I write this in the next line, these 3's are going to disappear on the left side, so I'm going to be left with just y on the left side. Great. And then on the right side, I'm going to get, well, basically exactly that. So we've got 2x minus 4 all over 3, and then all we're going to do as our very last step, so that we can really see how to get from here to something we can graph, is I'm just going to split this up into 2 fractions. So I'm going to take this 2x, I'm going to leave it as the numerator for one fraction, and we'll stick the 3 in the denominator here, and then we'll put that minus sign in the middle, and then we'll put our second fraction. So we have a 4 in the numerator, and the 3 in the denominator there as well. So notice that if I'm splitting the fraction, I can only split it if I've got addition or subtraction in the numerator. If I've got addition or subtraction in the denominator, it doesn't work. Like, you can't split it within the denominator. But what I've done is, I've taken the 2 numerators, I've taken the one numerator, and I've split it into 2 different numerators of 2 different fractions, and kept that minus sign in the middle right there. And the denominator just gets copied over into both places. So we've got 2x over 3, and then minus 4 over 3 over there. And if we rewrite this 2x over 3 slightly differently, we can take the 2/3 bit and sort of pull that away from the x, and then it looks like what we've got over here. So this equation ends up ultimately looking like that equation right there. And we know how to graph that, because if we look at the equation of a line, we know y is equal to mx plus b. We know what to do if we've got m. We know what to do if we've got b. And so we can see here that our m is this 2/3, and our b over there is this negative 4/3 over here. And so we would be able to then take that equation and graph it and get a visual representation of what this equation looks like. So on a test, I could ask you to do something like that. On your homework assignment, there is something exactly of this sort of nature. I've asked you to, except, yeah, I think it's quite similar. I've asked you to graph a linear function, but I've written the equation in a slightly different manner. So you have to do a little bit of work with the equation before you can actually graph it. But yeah, hopefully that answers the question that I posed to you at the end of the last video, which came out on Thursday, I believe. And I'm recording this one on Tuesday. I believe the last one, yeah, went online just after midnight on Thursday, and this one I'm recording it just after midnight on Wednesday. So this has been up on the board for a few days, so it's nice to finally have that question answered so I can erase it from here. Now, I was debating doing another example of finding the equation from a graph, but I think I'm going to change it up just a little bit for this particular video. I want to talk about the concept of negative slope in this video, and we might not actually do any proper examples of it in this video, but then in the next video we'll do a graphing example, or so far we've gone from the equation to the graph, right? So far this is what we've been doing. And we've done a little bit going in reverse. What I'm thinking is we'll introduce the concept of negative slope, and then we'll revisit at least one of each example. So we'll find the graph based on the equation, and we'll find the equation based on the graph, and then we'll just do more practice, probably mostly emphasized in this direction because we've done less of that so far, that I give you the graph and I ask you to find the equation. But I really want to talk about negative slope before waiting too much longer, because otherwise we keep doing examples with positive slope, and then you don't really get to see what happens with zero and negative slopes. So, yeah, so let's call this negative slope. Yeah, we'll just call it negative slope, because that's sort of the focus. We'll also talk a little bit about what happens if your slope is 0. So we'll put a nice happy face there. Great. So we're going to talk about negative slope in this video. So now let me just draw out a little bit of a Cartesian plane. You don't have to put a whole bunch of lines all the way across it, because I just want to highlight a key point about the behavior of lines with different slopes. So if I just sort of eyeball this, I'll just draw out, that's going to miss the origin, isn't it? So if I just draw out a couple of lines, so let me start off by drawing one that goes like this, pretty much straight except for up in that corner, something like that. So we have a line like this. We could say this line has a slope of 1, that it's at like an exactly a 45-degree angle with respect to our x and y axes. And so you could say that here the slope m is equal to 1. All right, now we examined what happens if you have a slope that's larger than 1. So if you have a slope of 2, your line would look something like this. Now obviously this is an approximate sort of representation of it, but this line right here is one with a slope of 2. Right? And that idea extends if you go, if you go here, this could be a line with a slope of 4 or something, let's say. So we know that as your slope gets bigger, your line gets steeper and steeper this way, right? As your slope gets smaller, like if we make it fractions, then if we wanted a slope of 1/2 and we wanted to graph that, that might look something like this, right? That might look something like that. M equals 1/2, right? This is just an approximate idea of what happens here. And then if we do one more, we could get something like this, and we could say that this has a slope of 1/4. Right? So we can see that if you've got a slope of 1, you'll have this line right here in the middle. Let me see if I can sort of emphasize this line a little bit. I'll just make it a little bit thicker, like so. Like so. So that was our line for a slope of 1. And then going down this way, our slope is getting smaller. And going this way, our slope is getting larger. So all of these ones have a slope larger than 1. And then all of those ones have a slope smaller than 1. Now, my question to you is, what happens if, I'm going to erase all of this now, this is just as a bit of a refresher of the behavior of lines with different slopes, but now hopefully you can see what happens with the different slopes that we've talked about. We're kind of limited to lines that look something like this. We haven't talked about what happens if your line is perfectly flat, perfectly vertical, or pointed downwards like that. So we're going to talk about those today. Negative slope is sort of in the spotlight, but those are 3 different cases. What happens when the line is flat, when it's perfectly vertical, and when it's diagonal but in the opposite direction. So first things first, let's look at a reasonably simple case. So we've got our Cartesian plane, which looks something like this, and we've got a line that's perfectly flat and is sitting up there. This is our x-axis, this is our y-axis. All right, so you can think of the slope as a measure of the steepness of your line. So if you were, if you had a hill and you're trying to walk up a hill, you've got something like this, and you've got a person trying to climb up a hill, they might describe it as having a steep slope or a shallow slope on the way up, and they could describe it differently going on the way down. But if you had at the other side of the hill, let's say you get to the other side and it's perfectly flat along the ground there, you wouldn't say that it's a shallow slope or a steep slope at all. You'd say that there is no slope to the ground that you're standing on, right? It's perfectly flat. There is no slope. And so this is true for our linear equations as well. The slope of a line that's perfectly horizontal is 0. And the way we can sort of see that is we know that if I had a line going, if I just draw them from here, if I had a line going that way, that's got a slope of 1, right? This has a slope of 1. That's an equal sign, not a negative sign. Let me make that clear. So we've got a slope of 1. If I go like this, we've got a slope of a half, right? Which is smaller than 1. But if I go here, that's going to be a line with a slope of a quarter. If I go here, that could be, let's say, like a slope of 1/10. I could get really, really close to having a flat line, and I could just end up with a line that's got like a slope of, I don't know, 1 over 1,000. I've got a slope of 1,000. It's almost a flat line, but it's not quite a flat line. But you can see what's happening with the value of the slope, right? As we start, let me clean this up a little bit. Let me get rid of the hill down here as well. As we start making the slope smaller and smaller, the line gets flatter and flatter, right? If I drew a line like this, we'd say it has a slope of 1. We would say that this has a slope of like, I don't know, like 1/5 or something. A line like this is almost perfectly flat, but not quite, right? It's a little bit above the x-axis over there. It's a little bit below the x-axis over here. It has a really, really small slope, and you could understand how, if you just drew this line for long enough, you'd see that you'd get a slope. Remember, your slope is rise over run, and you'd get a slope of, okay, well, I go up 1 unit, and then I have to go over, 50 units to the right or something until I can actually hit that line. So then you would end up with a slope of your rise is 1, and then your run is 50 or 500 or 5,000. You're getting really, really flat lines, almost perfectly flat lines if you if you go about it that way. And so that gives us an idea of what happens when you get to a flat line, which is that in order to get to the next point on the line, you so if you have a slope of 0, let me sort of, I think I was trying to jump a step there. You can see just from the behavior of the slope that the slope is getting really, really close to 0 as the line gets closer and closer to being perfectly flat. So it's a pretty safe assumption that when the line is perfectly flat, the slope is 0. Now, there would be some people in university math courses that would argue that I'm not explaining that as properly as I could, or I should be using specific words or specific notation or something to indicate exactly what I mean mathematically, but we don't really care because it kind of makes sense, right? If you were walking on perfectly flat ground, you would say there is no slope to the ground. If somebody asked you to quantify it, like with a number, what is the slope of the ground upon which you stand, and there is no slope that you can really detect, then you'd say there's no slope, there's 0 slope. And that's the idea with flat lines, is that the slope is 0. Now, you can also think about it in terms of this rise over run equation, right? This tells us that if we're given 2 points on a flat line, let me clean this up a little bit now. If you're given 2 points on a, well, there goes my entire line. If you're given 2 points on a flat line, so here and here, these points have exactly the same y value, right? These points, if they're exactly in line with each other, would have exactly the same y value. So if we look at our new equation for how to write out the slope, we had y2 minus y1 over x2 minus x1. And without actually plugging in any numbers, if you know that the y value of both points is the same, then that means y2 and y1 are the same value. So if I do one number minus itself, I'm going to be left with a 0 on top, right? So if I'm left with that 0 on top, then it doesn't matter what the denominator is, because 0 divided by anything, so 0 divided by, who cares what number goes down here, that's, let's put a question mark, 0 over anything is still going to equal 0, right? We don't care what we're dividing 0 by. 0 divided by anything is going to give us 0. So as long as we know that the y-coordinate of the 2 points is exactly the same in both of them, then we know our slope is 0. Now, obviously, if we were working with a more complicated function, you could have a function that, you know, it goes up and then it comes back down and then it goes up again. And so you would see that it has the same y-coordinate on a whole bunch of different points. So this idea doesn't work for functions like that. But if we're dealing with straight lines, if you can find 2 points that have the exact same y-coordinate, your slope is 0. So so what we're going to do next, so this has given us an idea of what it's like to have a slope of 0. Now we still need to talk about what happens if you've got, instead of a perfectly horizontal line, a perfectly vertical line, and then what happens if you've got a diagonal line but in the other direction. So let's erase this. So far we've explained what happens when you've got a slope of 0. Hopefully I've explained it decently well. I do apologize if I haven't. There's been a lot going on at the start of this week, but it's all about to calm down in about 2 days. So that should be pretty good. So we've talked about what happens when you've got a flat line. Now we got to talk about what happens when you've got, let's say, a line that looks like this. So here's our y-axis, here's our x-axis, and this thing over here is our line. All right, the line that we're interested in. And we'll say that this line is perfectly vertical. What is the slope? Let's remind ourselves, if we've got a line like this, this would be a slope of 1, right? If we've got a line like this, this is, let's say, a slope of 2. How big can we get before we hit this one? Because when we're going in the other direction, we went from 1 to a half to a quarter. You know, if you can pick it to, you can pick any fraction you want, right? 1/10, 1/100th, 1/500th, 1,000th. All of those numbers were getting closer and closer and closer to zero, right? We weren't just getting infinitely smaller, like infinitely more negative. We were getting infinitely close to zero without actually hitting zero. So we're like, all right, if your slope is basically you're going up 0 units before you have to move over. That's if you were looking at this from like a calculus perspective, which I know we're not doing. If you were looking at it from a calculus perspective, we're basically saying that in order to go from a line with a slope of 1 to a line with a slope of 0, you basically change your run to basically be infinity. So you have to go up 1 unit, and then you have to go over infinitely many units to the right in order to reach your next point. And if you were to try to graph that, most calculators would not be happy to graph this. But if you tried to get a calculator to describe what 1 over infinity is, chances are the calculator will tell you 0 is the answer. And the way you can think about that is if you have one cookie and you have to divide that cookie up between infinitely many friends, each person isn't going to get a cookie. They're not each going to get half a cookie. They're not even each going to get a crumb of a cookie. They won't even each get an atom of a cookie, because if you have like a billion atoms and just the one cookie, then you could only feed a billion friends if you gave each friend one atom. But if you've got infinitely many friends, then you have more than a billion. So effectively, each person gets none of that cookie. And so that's why if you treat this idea of 1 divided by infinity to basically just mean the same thing as 0, that's sort of the calculus way of thinking about this problem. Now, obviously, don't worry too much about thinking about things from a calculus type perspective. We're not worrying about that right now. That's sort of just sort of like a side comment. But what we are worried about is we're trying to figure out what happens if you're graphing a line that, instead of being perfectly horizontal like we were talking about before, is now perfectly vertical. And so that poses a different problem for us. So now we're not dealing with this anymore. And we're not dealing with a slope of 0 anymore, so I can get rid of that as well. The thing with the horizontal lines is that we were basically approaching a slope of 0 as that denominator got bigger and bigger, because 1/2 is smaller than 1, 1/10 is even smaller, 1/100th is even smaller than that, 1,000th is even smaller, a millionth is even smaller. And so basically, as that denominator gets bigger and bigger and bigger, the whole fraction gets really, really close to just being 0. And so what we've done is, if you make that denominator infinity, then your slope is basically 0. So it's kind of easy to see in that case, not so much if you're writing it down, but if you're thinking about it, it might be a little bit easier to tell that your slope is approaching 0 as that denominator gets bigger. But what's the biggest number that we could use in the other direction? Does it get really, really close? Like, does it go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Does it approach a specific number as we get closer and closer to a vertical line? Because a slope of 5 might look something like this, and a slope of 10 would look like that, but it still wouldn't be perfectly vertical. A slope of 100 would also almost look perfectly vertical, but not quite. A slope of 1,000 might look perfectly vertical, but it won't quite be perfectly vertical. So we can keep making our numbers bigger without bound, really, right? And what we find is that there's actually no answer. The slope of a perfectly vertical line, is undefined. So this is for a vertical line. Vertical a vertical line, your slope is undefined. So if you're not writing down too much right now, just because mostly I'm trying to talk you guys through the concept that we're working on here, that's okay.